basically I'm engineer, we are engineers. First of all, we try to see the mechanical influence, and it's sure that shear stress has some influence. But also it's a circle. Does shear stress just initiate activation, or just its force which develop on some kind of the cell? So it's still the question, but I think they are both probably. We have both signaling, also some kind of activation, which is influenced by shear stress, but also it's not, we cannot be sure that only shear stress is just a mechanical factor which influences on this one. So it's, I can say, very, very interesting research, and modeling of this biological problem, of course, still a huge issue. We are still, let's say, in the pioneer phase. We are still in child phase of this modeling, and we have to do a lot in order to address a lot of research, mathematical and algorithm approaches, and different model in order to try to make this experiment more understandable. Of course, when we talk about modeling, I like to say that also it's important that people from modeling design experiments. Why? Because they know what they put in model. For example, as I told you, modeling of thrombosis, actually platelet aggregation, very simple experiment. So we have just two plates, fluid, and inside the platelets, nothing more. No red blood cells, nothing more. No proteins, nothing. So then we can concentrate only on that problem. So only we have two materials, plasma and the platelets, and we have additional force of the binding of the platelets to the wall, and we have, of course, this conservative random force and this dissipatory force. So only one parameter is fitting, actually, the binding of the platelets to the wall. What is the force of the binding, and we fit it. And there are experiments which was done on the MIT University, and that experiments, if it's linear, it's around 50 Newtonian per square meter. So we are actually in the range. We got something like 80 or 100, but it's order of the range. So we were very happy about this because we didn't know that experiments about one single binding of that one. So if we are close in the order of the force of one single cells, we can say, okay, if we put billions of cells or put a lot of cells here, of course we cannot put billions because the computer power is still not possible, but we can simulate a small part. We can simulate, try to simulate the zone where we are of interest. Of course, you have, for example, huge blood vessel, which is times 3 millimeters, 4 millimeters, or even bigger. But we can run finite element on the whole domain, but only near the wall. We are interested only near the wall. What's happened? We can put this kind of simulation, this particle modeling, and DPD modeling. So I think this is just the beginning of the research, and I hope that I just gave you introductory presentation about this kind of modeling. And of course, the goal of the workshops is to exchange this kind of experience, and I will be very happy to listen your questions, especially from students, young students, and so ask questions. What not only me, of course, our guests from abroad, and try to think about this kind of problem. Maybe you will get a much better idea how to solve some problem, and or people from the experiment world. Please ask, and try, if you have some question about experiment, or maybe you're not doing experiment, but maybe we can say something, and maybe we can put something inside the question, and try together to understand this very, very complex task. So I'm open for your question. Thank you for your attention.
Somebody should break the ice, and that's me. Now, I have two questions. The first one is a comment. You are using this rotating plate to create a shear stress, which is a nice model, but it's far away from the situation in view. What is in additional model what could be used? We have in our lab. It's a pump created by the company EBD, and you could make a program what kind of shear stress we would like to have. We would like to have a constant one. We would like to have a pulsative one. What kind of how to say the step, how is going, and how steep is this shear stress, increasing, decreasing, all the parameters, and you could connect that one to the flow chamber. This flow chamber could create whatever you want. You could create a bifurcation. There are different profiles, and you coated them with the endothelial cells. It's simulating very nicely the blood vessels. You could put a particle, a small red fluorescent bead. We could visualize. So
it's experimental device.
Yeah, but there is quite a lot of data you could take from that one with the different shear stress condition, and after then to evaluate and prove the concept on the end.
Okay.
And the second one about the CAM assay in the pillar formation. Actually, this is my topic. And I know what I'm going to talk today. In that case, I will change now immediately my presentation. And what you demonstrate now, there are a couple of bifurcations. But it's very interesting the capillary plexus, because this process is taking place also in the capillary plexus. And this is because the bifurcation is quite easy. But in the capillary plexus, I think this is the challenge to say what's happened there. Because it's not only during the developmental angiogenesis, this process is taking a very important role in the resistance to the chemotherapy or radiotherapy, because the tumor, they are switching the way of angiogenesis was sprouting with this second type of etc. I think this is, in my eyes, in my opinion, it's a very, it's area with a huge potential.
Okay, but is it just, I don't know exactly, is it just complex geometry, what you say, or just...
No, in the capillary plexus, there is the pillars, they are rising not only at the bifurcation, they are arising in the capillary plexus as small meshes, and after that there is arrangement of these pillars, and after that they segregate, they give cut small capillary segments. And in this way, the tumor...
Can you approximate it in 2D or not?
Yeah, of course.
Ah, okay, awesome. That's even better, because in 3D...
Absolutely. Absolutely.
Okay.
This is the first step to the tumor vasculature, which has more or less the same shape and the same problematic.
Because all the images are actually 2D, so it's maybe it's easier to try 2D than maybe some complex model to develop. So you have all these slices?
I'm going to show today. I don't know what I'm going to show today. And what is important now, because most of the people from the biological point of view are interested in molecules, in genes and molecules. And 90, I would say even more, 95% of the scientists, they are working in the field of angiogenesis, they are working exactly on that one. And just a few people worldwide, a few labs are working on the hemodynamics, which in my opinion is a very important factor by the, even in the tumor angiogenesis. And there is such kind of balance or interplay between molecules and hemodynamics. And nobody until now was able to have a complex view or the complex concept on this interaction between the molecules and the hemodynamics. This is the challenging story.
Yeah, so I think that's the reason why we are here. I mean, we have to discuss and try to make good ideas and try to make. So do you think, but this kind, you said molecules, are you talking about chemical reaction by chemical binding?
Growth factors. I talked about the different growth factors.
Growth factors.
Yeah.
Okay. So, but how to put in the model?
No, but you could in my opinion, it's a very easy story, because you have a model, you have a chemodynamical, you could change a chemodynamical condition even in a model, and you could interfere in that moment with the different factors. One putting one, inhibiting another one, or inhibiting the same, and playing with that one all the time, and evaluating changes.
What is the initiator? Mechanical forces, or who initiates the process?
What do you think?
Growing.
This is quite a complex process. This is an interplay between two systems, the chemodynamical forces and growth factors. Most likely the growth factors are initiating, but the mechanical forces are very important. Or if you increase the shear stress, they are responsible for production of some mechanical, some growth factors. I think it's going by that.
Okay, thank you very much for the discussion. Somebody else? Yes.
Very impressive overview there. I had a question about the way you model the deformable particles. You showed these nanoparticles that were flowing, that were also deforming.
Yes.
Was it also by means of DBT or how?
No, this is continuum. What you see just continue. The particles.
Yes.
It's going to microvessels, continue, completely everything continue.
Okay. Because if I understood correctly, in the case of DPD, the particle itself is actually undeformable.
Yes,
correct?
correct.
Yeah.
Correct. But if you want to simulate, for example, red blood cells, it's not just one particle. You can collect this, the group of the particles with some springs.
Springs, okay. And then
So
these springs
they can deform.
Right,
yeah, of course. That's for red blood cells, because red blood cells is a huge cell, not small cell.
For the movement of the platelets, so in the case of the application of DPD, that problem, one particle is one platelet, I guess.
One particle, yes, exactly.
But they do not have any rotational degrees of freedom. Could that be important or not?
They are rotate, of course, because they're moving. They completely rotate, and we have additional forces because rotation. This is viscous force, but also there is a force because rotation.
Okay.
So it's two additional. Yes.
All right. So that is.
Yeah.
That is being. So you also have an equation for angular momentum. Then.
Yes,
okay.
of course. Yes. It's actually work from physicist. I forgot the name from Spain. It's very famous. He actually established DPD method for this kind, introduced these additional forces and etc. for physics. So that's very interesting. And then we put this methodology and add forces between platelet and between platelet and the wall, the binding actually. So it's still mechanical approach, I agree, but can work in this situation, in this kind. Any other questions? So okay, I think in the schedule we are now on the coffee break. So 15 minutes break, then we will continue.